So for the past 15 years, I am working with the resonant converter. Okay, what are the problems we have faced and challenges? Uh, how to eliminate the issues? So these are the problems we have identified. How to eliminate the problems? So for uh, the 15 minutes, sorry, 45 minutes, we will discuss. Okay. So first of all, I would like to welcome the president of this webinar, Dr. Abdullah sir, and our respected principal, Dr.M.Periyasamy sir, for this webinar, who is supporting and inspiring us to organize many useful events for the development of student community. I am very happy in welcoming the Dr. N. Karthikeyan, HOD in PG of CSE department of our college, who is uh, instrumental for organizing this webinar. I am very happy in welcoming the coordinator of this webinar, Professor Dr. R. Nagarajan, Professor P. Nedumal Pugalendi, Professor G.T. Arun Prasad, and all the faculty members of our department. Last but not least, I welcome all the energetic and enthusiastic participants for this webinar. Right. Arun, go to slide.
I request all the participants to pinpoint the presentation slide. Sir, visible இருக்கா சார்?
எனக்கு இன்னும் வரலையா அருண்?
இல்லையா சார், visible இருக்கு.
வந்துருச்சு அருண், வந்துருச்சு. ஓகே
ஓகே
ஓகே. So research issues and challenges in resonant converter, right? So first introduction about the DC to DC converter, right? So DC to DC converter is an electrical circuit that transfers energy from a DC voltage source to load. The energy is first transferred via electronic switches to energy storage devices and then subsequently switched from storage into the load. The switches are transistors and diodes and controlled devices, transistor, MOSFET, and IGBT, right? The storage devices are inductors and capacitors. The process of energy transfer results in an output voltage that is related to the input voltage by the duty ratios of the switches. It is insightful and worthwhile to investigate why DC to DC converters are necessary before their detailed presentation and analysis. In addition to the constraints of size, weight, and cost, DC to DC converter technology also addresses the issues of efficiency and regulation. Right. So before we are going to entering the topic, first I ask one question. Consider a power supply design problem in which 5 volt DC at 4 ampere must be provided from a 12 volt DC supply, right? So one solution is to use a resistor to drop the 12 volt down to 5 volt. So the input voltage is 12 volt. Our required output voltage is 5 volt, right? The calculation is the required resistance is 12 minus 5 divided by 4 is equal to 1.75 ohm is the source resistance. And the load resistance, how to calculate? So 5 volt is required output voltage divided by 4 ampere current. So we got 1.25 ohm. So 12 volt DC input is 12 volt and output, our required output is 5 volt. How to get the 5 volt? So here 1.75 ohm resistor is the source resistor and 1.25 ohm is the load resistance. So the voltage drop across 1.75 ohm resistor and 1.25 ohm resistor. So we get output voltage from across the 1.25 ohm resistor for 5 volt. So here two major issues are associated with the circuit. Next slide, Arun. So the first is efficiency. The power required by the load is so 5 voltage and current is 4 ampere. So we get 20 watts. However, the power that must be supplied by the sources is 12 into 4. So 12 multiplied with 4. 12 is input voltage and 4 is the uh, current. So 48 watts. So input power is 48 watts and output power is 20 watts. So which results in an efficiency of only 20 divided by 48. So approximately 42%. The low efficiency is due to the power lost in the dropping resistor. So the dropping resistor is source resistor 1.75 ohm. So I square R. So 4 square into 1.75, we get 28 watts, right? So more energy is lost in the delivery of the power than is absorbed by the load. So this is the one. Efficiency is the first problem, right? Second problem with the circuit, the lack of regulation. It is rare that a primary source is absolutely constant. For example, the voltage of a 12 volt automotive starting battery can vary as much as plus or minus 12 volt. So depending on whether the battery is being charged 14 volt or if the car is started while the head and tail lights are on, so it's go down 10 volt. So 12 volt input supply is varies from plus or minus 2 volt. So whether 14 volt or 10 volt, if the source in the circuit drops to 10 volt, the output voltage would drop to 4.2 volt. So our record output voltage is 5 volt we need, but input voltage variation 10 volt. The input is 10 volt. Then the output voltage is 4.2 volt. So if the source is increased to 14 volt, the output increases to 5.8 volt, 5 to 5.8 volt. So these voltage fluctuations could cause severe functional problems for the load, especially if the load is a circuit based on the 5 volt logic technology. To overcome the efficiency and the regulation problem, a control scheme must be introduced whereby the output voltage is measured and the supplied energy is varied in accordance with the requirements of the load. If the source voltage increases, the controller must decrease the source current to prevent an increase in load voltage. Decreased source voltage requires an increase of output current to keep the output voltage constant. Okay. So next slide, Arun. So we are going to resonant converter, right? So these two major problems, one is the efficiency and the regulation problem. So we are going to controlled converter, right? So why we are going to resonant converter, or what is meant by resonant converter? Resonant converter means at least one resonant tank circuit as a sub-circuit, and the sub-circuit consisting of at least one inductor and one capacitor, right? So in recent years, the design and development of various DC to DC resonant converters have been focused for telecommunication and aerospace application. It has been found that these converters experience next slide, Arun. Next. Found that this converter experience high switching losses. So previous slide. Okay. High switching losses, reduced reliability, electromagnetic interference, and acoustic noise at high frequencies. So next slide, Arun. Next. So that previous slide, please. So LCL resonant converter. Here 3 types of resonant converters are there. So before, if suppose we are using 2 energy elements like L and C, right? One inductor and one capacitor, it is called second order resonant converter, right? So here third order resonant converters, 3 storage elements we are using. So LCL, the configuration type is T type, and LCC resonant converter. So LCL resonant converter means one inductor, two inductor and one capacitor connected in series, right? So it is called series resonant converter. So LCLT resonant converter is two inductor and one capacitor connected in T type. So it is called LCLT resonant converter, right? So LCC resonant converter, we are using two capacitor and one inductor, right? So the series parallel resonant converter circuits are the basic resonant converter topologies with two reactive elements. A series parallel resonant converter is found to be suitable due to various inherent advantages. The merits of series resonant converter include better load efficiency due to the series capacitor in the resonant network and the inherent DC blocking capability of the isolation transformer. However, the load regulation is poor and output voltage regulation at no load is not possible by switching frequency harmonics. On the other hand, parallel resonant converters offers better no load regulation but suffers from poor load efficiency due to the lack of DC blocking for the isolation transformer. Hence, and resonant converter with 3 reactive components is suggested for better regulation. Right. Arun, slide. Arun, slide please. Right. So the LCL tank resonance circuit based DC to DC resonant converter has been experimentally demonstrated and reported by many researchers, right? So it is obvious from many literature works that the output voltage regulation of the converter against load and supply voltage fluctuations has an important role in designing high density power supplies. The LCL resonant converter is expected to have fast response, better voltage regulation, and improved load independent operation. Motivated by these facts, the LCL resonant converter has been modeled and analyzed for estimating various responses. The closed loop models have been simulated using MATLAB Simulink for comparing the performance with the existing control techniques. Study of various literature works reveals that microcontroller is being used to develop the two inverts required for driving the switches of the two legs of the single phase inverter. In a closed loop system, an analog to digital converter is required to monitor at least any one of the system parameter, usually the terminal voltage on the output DC side. Hence, with a single microcontroller, it is impossible to carry out the two jobs of monitoring and controlling independently. So, with the advent of the advanced RISC microprocessors, we can do many tasks in parallel. The operating system loaded onto the aforementioned processor has a facility that makes it possible to carry out multiple tasks. So, RTOS stands for real-time operating system. It overcomes to a certain extent the drawback of the von Neumann architecture that uses the fetch, decode, execute sequence. With RTOS, a number of tasks can be carried out in a near simultaneous manner. The processor LPC2148 has two sets of analog to digital conversions So one is ADC 0 and ADC 1. ADC 0 can handle 8 channels, while ADC 1 can handle 6 channels. All these channels can work independently. Typically, a multiple input, multiple output system can therefore be controlled by LPC 2148. The gap between the MIMO system design and implementation is reduced. So next slide. So this is a block diagram of an LCL resonant converter. Unlike the conventional resonant converter that has only two elements, the proposed resonant tank has three reactive energy storage elements, that is LCL, right? The first stage converts DC voltage to a high frequency AC voltage. The second stage converts the AC power to DC power by a suitable high frequency rectifier and a filter circuit. Power from the resonant circuit is taken either through a transformer in series with the resonant circuit or in parallel with the capacitor comprising the resonant circuit. In both cases, high frequency feature to the link allows the use of high frequency transformer to provide voltage transformation and ohmic isolation between the DC source and the load. In an LCL resonant converter, the load voltage can be controlled by varying the switching frequency or by varying the phase difference between the inverters. The phase domain control scheme is suitable for a wide variation of load condition because of output voltage is independent of load. The absence of DC current in the primary side of the transformer does not necessitate the requirement of current balancing. Another advantage of this circuit is that the device currents are proportional to load current. This increases the efficiency of the converter at light loads because there is the reduction in device losses. So the resonance circuit consists of series inductance L1 and a parallel capacitor C and a series inductance L2. The switching devices S1, S2, S3, S4 having gate turn on and turn off capabilities. The gate pulses for S1 and S4 are in phase but are at 180 degree out of phase with respect to the gate pulses for S2 and S3. The positive portion of the current flows through the MOSFET and the negative portion flows through the anti-parallel diode. The load resistive or inductive or capacitive or RLE is connected across bridge rectifier via chopper L0 and C0. Right? The voltage across the point AB is rectified and fed to chopper circuit. Load is connected through L0 and C0 in the analysis that follows. It is assumed that the converter operates in the continuous conduction mode and the semiconductors have ideal characteristics. Sir, please go to next slide. Next. Next. Right. So, steady state stability analysis. Right. So, here transfer function model of LCL, LCC and LCLT resonant converters. Here we are taking three topologies. So, one is LCL, another one is LCC, and the third one is LCL-T resonant converter. So, first DC to DC converter. So, conventional converter without controlling devices, we are using how to 12 volt supply is converted into 5 volt. The time we are using two resistors, right? One is source resistance and another one is load resistance, right? That case, problem is efficiency and voltage regulation, right? So next, conventional DC to DC converter. So buck converter, right? Here we are using one MOSFET switch. So 12 volt is converted into 5 volt because of duty cycle, right? Here also we have some problems, the efficiency and voltage regulation. right? So compared to previous one, without controlling devices, the efficiency is 48%, right? 48 or 42%. So we are using controlling device. The buck converter efficiency is 70 to 80%, right? Depends upon the load. The conversion efficiency is differ, right? Next we go to resonant converter. So second order resonant converter. So here some drawback is there. So isolation transformer and high gain transformer we need. So we are going to third order resonant converter. So here three topologies we analyzed. One is LCL, LCC and LCLT resonant converter, right? So energy storage elements we are using. So stability issues also there. So what are the stability issues we will discuss, right? So first transfer function model of LCL, LCC and LCLT resonant converter, right? So some assumptions are there, right? Or 7 assumptions. So the equivalent circuit. Sir, go to next slide. So this is the LCL resonant converter equivalent circuit diagram. So L, C, L are connected in series, right? The equivalent circuit. Okay, the vector space equation for the converter is X dot is equal to AX plus BU. The state space equation for the LCL resonant converter is obtained from this figure. Go to next slide, sir. So these equations to right. So from the aforementioned equation, it can be concluded that the output voltage is not dependent on the load resistance and the converter gain follows a sine function. In order to maintain the output voltage constant at a desired value against the variations in the load resistance and the supply voltage, the pulse width has to be changed in a closed loop manner. However, the required change in pulse width is very small, right? Next slide, sir. Next slide. All right. So design of resonant converter. So in order to pursue the analysis, a converter with specifications, following specification is designed. Power output is 133 watts. Minimum input voltage 125 volt. Minimum output voltage is 100 volt. Sir, previous slide, please. So next slide. Right. So the high frequency transformer turns ratio is assumed to be unity. So from the equivalent circuit, the load impedance value is 75.18 ohm, and LC value are L1 and L2 185 microhenry, and C is 0.052 microfarad, right? So from figure 2 of this equivalent circuit, applying the Kirchhoff's voltage law, we get the transfer function of the LCL resonant converter. So N V naught of S divided by M V of S is equal to ZL CS divided by S square into L1 plus L2 into C plus ZL CS plus 1. So apply the values of L1, L2 and C. We get one transfer function, right? So next slide. So similarly, equivalent circuit of LCC resonant converter, L and C are connected in series with the output, and last C2 is parallel with the load, right? So this is the equivalent circuit of LCC resonant converter. The same way we find the transfer function model, right? So next one, LCL-T resonant converter. So next slide. Next. This is the LCL T resonant converter. So equivalent circuit of LCL T resonant converter. Right. Next, sir. Okay. So the transfer function of LCL, LCC resonant converters are of order 2, and that of LCL T is of order of 3. From the basic principles, we know that if order of the system increases, the system will go to an unstable region. We feel that it is very essential to study the performance of resonant converter when the load varies. Hence, the following discussion briefs the steady state analysis of LCL, LCC, and LCL-T resonant converter, determine their ability. Right. So, go to next slide, sir. Okay. Stability analysis using root locus. Right. So, for the transfer function of LCL, LCC, and LCL-T, the root locus plot and the Nyquist plot also we found prepared using MATLAB coding. Right. The locus path is lying on the left half of a spline. So the LCL resonant converter is stable system. Right. So next slide. So root locus plot for LCC resonant converter. Here the locus path is lying on the imaginary axis of the spline, and hence the LCC resonant converter is a marginally stable system. Right. So next slide, sir. Here locus path of LCL-T resonant converter are lying on the real axis of the spline and the right half of the spline. Hence, LCL-T resonant could be considered as a unstable system. Right. So next, stability analysis using the Nyquist plot. So next slide. So next slide. So next slide, sir.
Sir, 2 minutes, sir.
Okay.
I'll be
Okay,
landing. Power cut
okay, sir. Okay. The conclusion regarding the stability of the LCL resonant converter can be proved from the Nyquist plot in next slides, where the locus of roots does not encircle -1 plus J0. But for the Nyquist plot for LCC, shown in next slides, it encircles -1 plus J0, which is one of the criteria for an unstable system. The Nyquist plot of the LCL-T resonant converter encircles -1 plus J0 twice, hence the system is said to be unstable. For determining the stability of the 3 types of converters, all possible studies were undertaken. Since LCC fails in all the stability studies, it has not been opted for further analysis. Moreover, LCL-T passes through Lyapunov and root locus stability analysis, but its failure in Nyquist forces us to come to a conclusion that in real cases, the stability margin will be less than the LCL converter. Hence, only LCL resonant converter has been opted for further analysis in the study. Right. So, one reviewer, IEEE, this work published in IEEE Transaction and Power Electronics So first, initially we are stability analysis using root locus, Nyquist plot, and Liouville stability. So one reviewer asked, what about state plane analysis of the LCL resonant converter? So,
Excuse me, sir. A presentation on this, sir.
okay, sir. So this is an Nyquist plot for LCL resonant converter, right? Here, where the locus of roots does not encircle -1 plus J0, right? Which is one of the criteria for stable system, right? So next, so this is the LCC resonant converter. It encircles -1 plus J0, which is one of the criteria for an unstable system. Right. Next, so this is a Nyquist plot for LCLT resonant converter. Here, 1 plus J0 encircles 1 plus J0 twice, hence the system is said to be unstable. So from the study, LCL resonant converter has been opted for further analysis in this study, right? Next slide. Next. So one review here, what about state plan analysis of LCL resonant converter? So on that case, we are using B plan, right? Phase plan analysis graphs, the linearization about the equilibrium points, right? So in that case, the LCL resonant converter has two state variables. One is IL1 of T and another one is VC of T. We got the state plane of the LCL resonant converter using P-plan tool. So the tool name is P-plan, right? For the LCC resonant converter, the solution plot converges to 0, for all initial conditions. And lambda 1, eigen vector lambda 1, lambda 2 less than 0. So we could conclude that the solution of the equation approaches to the origin as T increases, so thereby said to be asymptotically stable. Stability analysis of a FLC and stability analysis of FLC based LCL resonant converter are briefly discussed in next session. Right. So next slide, sir. So design of LCL resonant converter. Previously I told, right? The input voltage 125 volt and record output is 100 volt. The output power is 133 watts, right? So next. So from this equation, we design the L1, L2 and C value, right? So next. Right. So development of the PI controller. Right? So controllers based on PI approach, the commonly used for DC to DC converter applications. Power converters have relatively low order dynamics that can be well controlled by the PI method. So PI based closed loop simulating diagram shown in figure, right? So next slide. Next. Right. So the design of PI controller, Ziegler and Nichols conducted numerous experiments and proposed rules for determining values of Kp and Ki based on the transient response of the system. It applies to an resonant converter with neither integrator nor dominant complex conjugate poles. Right. whose unit step response resemble an S-shaped curve with no overshoot. This S-shaped curve is called the reaction curve, right? So from the Ziegler-Nichols tuning rule, proportional gain constant Kp is equal to 0.05 and integral time constant Ki is 25 are obtained for the converter under study. The system is simulated with the switching frequency of 50 kHz. It is observed that the PI controller for the LCL resonant converter regulates the output voltage with a settling time of 0.1 millisecond. So then we go for design of fuzzy logic controller, right? The fuzzy logic controller provides an adaptive control for better system performance. Fuzzy logic is aimed to provide a solution for controlling non-linear process and to handle ambiguous and uncertain situations. So fuzzy control is based on the fundamentals of fuzzy sets. The fuzzy controller suggested in this study takes error indicates small e and the change in error small c, right, as its input parameter, and the change in duty ratio capital D of the converter as its output parameter. So the fuzzy control scheme is implemented in this DC to DC converter and the results were recorded. Right. Next slide, sir. The next slide. Right. So the LCL is modeled by using MATLAB software. Fuzzy control is developed using the fuzzy toolbox. The fuzzy variables E, CE, and D are described by triangular membership function. Right. 7 triangular membership functions are chosen, and next table, one fuzzy rule matrix table is there, right? So fuzzy memberships, NB, negative big, negative medium, negative small, 0, positive small, positive medium, positive big are defined as, okay. So next slide, sir. So fuzzy rule table and inference engine. The rule firing contains the following steps, right? So from the membership function of input 1, the lingual under whose range the actual values is present is found. Also, its decimal height degree of belief is obtained. From the membership functions of input 2, the corresponding lingual is also found along with the degree of belief, right? For these two inputs, the output is fetched from the rule matrix, right? So next slide, sir. Right. This is a fuzzy rule matrix table, right? Next slide. So development of fuzzy logic control, right? At every sampling interval, the instantaneous RMS values of the sinusoidal reference voltage and the load voltage are used to calculate the error E and the change in error CE signals that act as the input to the fuzzy logic controller. The stages of fuzzification, fuzzy inference, and defuzzification are then performed by the program as described in the flowchart. Right. So E is equal to reference voltage VR minus load voltage VL, and change in error equal to E minus previous error, error minus previous error, where VR is the reference or desired output voltage and VL is the actual output voltage. The VT ratio of the converter will be determined by the fuzzy inference. For instance, if the output voltage continues to increase gradually while the current is low during the charging process, the fuzzy controller will maintain the increase in voltage to reach the set point. A drop in the output voltage level triggers the fuzzy controller to increase the output voltage of the converter by modifying the duty cycle of the converter. The resolution of an fuzzy logic controller system release on the fuzziness of the control variables, while the fuzziness of the control variables depends on the fuzziness of the membership function, of their membership function. Right. Next slide. Right. This is the flow chart for. So first read the voltage and set reference voltage, calculate fuzzy values for each input. Right. So if suppose VL equal to VR, load voltage equal to reference voltage, then go to stop. This condition is not satisfied. If suppose VL is greater than VR, find the error. So E is equal to VR minus VL. Find the change in error. Check all the rule values. So fuzzy controller 1 action and calculate duty cycle. Then PWM signals to chopper. Right. So if suppose VL is not greater than V, find error and check all the rule values. Fuzzy controller 2 action and calculate modulation index. So fuzzy controller 1 is duty cycle controller, and fuzzy controller 2 is modulation index. So inverter side controller, and fuzzy controller 1 is chopper side controller. Right. So next slide, sir. So this is a closed loop simulating diagram of a LCL resonant converter using fuzzy logic controller. Right. Depending on error and the change in error, the value of change of duty cycle is calculated. Set parameter instruction and the function blocks available in MATLAB are used to update the new duty cycle of the pulse generators. The closed loop simulating diagram of the LCL resonant converter using an FLC is shown in slide. Right, the entire system is simulated with a switching frequency of 50 kHz. It is observed that the FLC for LCL regulates the output voltage with a settling time of 0.06 millisecond. So previous case we are using PI controller based LCL resonant converter. The settling time is 0.1 millisecond. So fuzzy logic controller, if suppose we are using fuzzy logic controller based LCL resonant converter, the output voltage settled with 0.06 millisecond. Next slide. Next. So this part is overall results and discussion part. So the performance of fuzzy controller was compared with that open loop response, PI controller based LCL resonant converter, and fuzzy logic based resonant converter. Right. So first one is open loop response. Under the open loop condition with manually adjusted pulse widths of the converter switching for reference voltage of 100 volt, the output voltage of the system was 95 volt. The overshoot and the settling time are very high, and also the response is oscillatory. So that's why we go for closed loop system and using PI controller. Right. So next slide. Next slide. Right. So PI closed loop response with the PI control method for the same reference set point voltage, the output voltage was observed was 99.2 volt in the closed loop using a PI controller. The overshoot and the settling time are less compared to the open loop and also less oscillatory. So the slight drop in the resonance characteristics is due to the increase in condition losses in the bridge inverter and resonance network. So that's why we go for FLC based resonant converter. Here the output voltage while using an FLC closed loop system for a set voltage of 100 volt is 99.6 volt. While using this controller, the overshoot and settling times are less compared to open loop and PI controllers, and the response is less oscillatory. The harmonic performance of the AC components present in an output voltage is significantly improved compared to that of the PI controller model. The simulated values for open loop LCL and closed loop resonant converter have been estimated in the next slides. Right. The results of the simulation also verified and validated using the experimental setup. Right. This is a summary of dynamic response of LCL resonant converter for open loop response. The rise time. So the minimum for fuzzy control 0.055, right? Settling time also 0.04, and the steady state error is 0.014. Next slide. This is a simulated output voltage for current and voltage waveform with 100% voltage, right? So next slide, sir. Next slide. So this is a prototype model for a closed loop LCL resonant converter. So next slide. So this is the experimental result showing output voltage. Top waveform is voltage waveform, and the bottom one is current waveform for 100% load. Right. Next slide. So performance evaluation of hardware setup. So from the above comparison, it could be concluded that the FLC exhibits better performance in terms of reduced settling time, rise time, and peak overshoot. Next slide, sir. So experimental results showing startup response and transient response for 50% load using PI controller. Right. So it shows a settling time during the startup response of 0.058 millisecond, and when suddenly loaded at the time period 0.1 millisecond. Right. So the startup response of 0.058 millisecond will be settled. Then 0.1 millisecond we will give the disturbance, right? Then the transient response gets settled in 0.15 millisecond. So the aforementioned responses, right? So next one is FLC based for 50% load. We are using FLC controller, right? So here startup response and transient response for 75% load using PI controller. Right. So 50% of load using an FLC, it shows a settling time during the startup response of 0.05 millisecond. And when suddenly loaded, the transient response gets settled in 0.415 millisecond. Right. So previous PI controller technique, the startup response 0.058 millisecond, and when suddenly loaded at the time period of 0.1 millisecond, the system settles at 0.18 millisecond. Right. So the same as 75% load we tested It shows a settling time during a startup response of 0.057 millisecond, and when suddenly loaded at the same time period, the system settles at 0.148 millisecond. Right. So from the comparison, FLC based resonant converter is better performance. Right. So experimental results shows that fuzzy controller based LCL resonant converter is more robust against input voltage and load resistance variations than the PI controller. In conclusion, the fuzzy controller can achieve a better performance than the PI controller. Thus, the fuzzy controller design method is highly suitable for application of LCL DC to DC resonant converter. Right. So, previous slide, please. So this is a plot for percentage efficiency whereas output power in watts. Right. So the result obtained indicate FLC is an effective approach for the output voltage regulation of the LCL DC to DC resonant converter. So this slide shows the variation in percentage efficiency with the output power in watts. It is interesting to note that the maximum efficiency occurs at a load of 133 watts, for which it has been designed efficiency calculation for 100% load. So next slide. So efficiency is output power P out divided by output power plus total losses. So here output power we get 133 watts, right? Total loss is 10.29 watts. So this total loss includes switching power loss and switching power loss includes turn on loss plus turn off loss, right? So from this we get the efficiency is 92.83%. Right. So next slide. So conclusion. The LCL resonant converter has a better stability margin compared to other two topologies, LCC and the LCLT resonant converter. After the detailed stability studies using Lyapunov, root locus, Nyquist, and the state plane analysis, fuzzy controlled closed loop control system stability was also analyzed using in the Z plane. Right. Both FLC based and PI based LC resonance circuits were simulated using method of simulating and also experimentally verified by implementing the ARM processor LPC 2148. Right. The next slide. The FLC provides. Previous slide. The FLC provides better voltage regulation even under sudden variation of load. The reduction in switching power loss enhances the efficiency. The dynamic response and the steady state errors of fuzzy logic controller as compared with the PI controller and the open loop were determined by simulation and verified by experimental studies. Right. At full load, an efficiency of 92.83% was obtained. As the load was decreased, efficiencies remained high. However, at 11% load, the efficiency of the circuit was measured as 79.9%. An added advantage of FLC is that with minor modifications, the same controller coding could be extended to control any type of DC to DC converters, since their behavior can also be described by the similar set of linguistic rules. Right. So next slide. So this is research challenges in resonant converter. Right. So what are the basic requirements? Resonant DC to DC converters are used when high voltage gain is required. Okay. So transformer in between the source and the load sides, we need high voltage gain, right? And the next, resonant DC to DC converters are used when we need isolation between the source and the load, right? So transformer-less resonant converter is also available. That is parallel resonant converter. The output is AC, right? DC to AC converter. We are using transformer-less resonant converters, right? That is resonant converters are used when bidirectional power conversion is required. Right. Next slide. So the challenges include the saturation of the core of the transformer. So this is the one major issue. The transformer core is for particular condition, it will be saturated. Non-linear dynamics of the transformer, right? So non-linear dynamics of the transformer core also saturated, right? A need for large number of power electronic converters, right? More switching and core losses, conducted and radiated noise, right? So next. So modern developments. So usage of cascaded resonant converter. So the block diagram previously we seen 1:1 transformer we are using. If suppose 1:2 transformer, so another one secondary is there. So this is modular multi-level DC to DC resonant converter, right? So different voltages. So if suppose we are using electric vehicles or electric car, so starting purpose we need 12 volt DC supply, and wiper we are using 12 volt DC, and light headlight we need 6 volt, right? So that purpose we are using this resonant DC to DC converter, right? So usage of, right? So previous slide, please. So usage of novel and improved material for core of the transformer, right? So if suppose the core is saturated, so to avoid the saturation of the core, novel and improved material for core of the transformer, right? So multiple input, multiple output resonant converter topologies, right? So secondary side we are using 1:3 transformer. So 3 output levels we obtained, right? So transformer-less parallel resonant converter, like the one we have developed, right? So parallel resonant converter mean not DC to DC converter, it is DC to AC converter, right? So next slide. So control aspects, control of modulation index on the input inverter side, control of modulation index on the rectifier side, dual control on input and output side, novel tuning techniques of PI controller for output voltage regulation, non-linear controllers we are using, side mode controllers and other controllers. Right. So thank you. Thank you for patiently listen for the past 55 minutes. Thank you very much.
Before that, if you have any queries, I request all the participants to post your queries in the chat box. And a small summary, I think there is no question so far. A small summary about this webinar. The webinar, the total participants for this webinar is so far, as per the Google Meet attendance, 68 participants and 276 registered. Out of 276, 68 has been participated for this wonderful webinar. May I request Professor Dr. Nagarajan sir, on behalf of the Department of Electrical and Electronics Engineering, to propose the vote of thanks. Nagarajan sir, please sir. Sir, please unmute yourself, sir. Nagarajan sir, please unmute yourself, sir. Nagarajan sir, you are not audible, sir. Please unmute yourself, sir. And the feedback link is in a chat box. I request all the participants to fill the feedback form and get your certificates uh, from your registered mail ID. Okay. Mutlakshmi madam. Mutlakshmi madam, can you please unmute yourself? Dr. Mutlakshmi madam. So Nagarajan sir.
Hello, it's audible, everyone?
No, okay, sir. Audible, sir. Audible, sir.
Audible.
Proceed, sir.
Okay. So, good morning to all. I sincerely thank our principal who has given all the support and continuous encouragement for us to conduct the development activities like this webinars and all other activities, program and all other activities. I wholeheartedly thank our convener and the resource person of today's program, Dr.S.Selvaperumal, who has presented very nicely about the research issues and challenges in resonant converter. So definitely this will be helpful for the participants to go ahead in their research, sir. Thank you very much, sir. I also thank the PGHOD, Karthikeyan and Arun Prasad for taking sincere efforts to organize this webinar. And I also thank the faculty members faculty members and non-teaching staff who directly and indirectly involved in making this program success. And last but not least, I thank all the participants who effectively participated in this program. Without you, this program may not be successful. And finally, I thank one and all for attending this wonderful webinar. Thank you all.
Thank you all.
Thank you, sir.
The
Thank you,
session will
Arun.
be live for. Sir, thank you, sir. Session will be live for 2 minutes. Those who are not completed the feedback form, I request you all to complete the feedback form.
Arun, shall I leave?
Okay, sir. You can leave, sir.
Okay.
Thank you, sir.
Arun.
Thank you, sir.
Thank you.
அருண் லிங்க் மறுபடியும் கொஞ்சம் போட்டு விடுங்க அருண் எனக்கு. நான் தேங்க்யூ.
Post பண்ணிட்டேன், sir.